So what I wanted to bring you a bit today is not one specific paper, but a set of papers or some things that can be connected together. So my objective is to get a topic and try to look around that topic from the different angles, and that's why we talked with Mickey that it kind of became a string of things that you can try out. String of things because I think it represents a kind of problem domain, and you can tackle from this angle, that angle, and try to come up with the solution that fits you. A moment about why I wanted to choose this topic, but before it, who am I? Who didn't meet me yet? I'm professionally, I've been a CTO and the lead of research for long years in startups, but technically what I do now is I teach at the Frankfurt School of Finance and Management. I teach management people, and I teach people to code deep learning classes and NLP classes, and I do Budapest AI, so that's the community outreach part that I'm doing. Okay, why? The big motivation is here, kind of like, yeah, that wasn't me, that was Chris Takio, who said that, I mean, yeah, your thing is not that big. In the sense of people are talking about big data, but what I included here is a search from Google Trends. So yeah, there was definitely a big hype going on with big data, but I think sooner or later people realized that it's not everything. So it's not true that in each and every case you go into a corporate and you already have a big data situation. Many times I did consultancy, and what we found out is that when we ask a manager whether you are in a big data situation, he naturally says yes. And the reasoning behind it doesn't fit into Excel. It really, I mean, it's over 65,000 rows, and that's big data. I mean, bigger than my head, isn't that? So that means that many times you find out that you are not in a big data situation, and although people are rolling out infrastructure for teaching huge models on big data situations, many times the really interesting business problems are having not enough data. So that's the big motivation why I wanted to bring this topic, because if you go in and do data science, it happens to be that you are many times doing not big data. Okay, what are the assumptions? What I would like to challenge you a bit is to think about what the underlying assumptions about our modeling efforts are. Our underlying assumptions are that we have some kind of distribution, the distribution of all possible kitty data, like all the possible images about kitties in the universe, which is an abstract entity, and we draw a sample from this, and we are very satisfied because we think that we drew enough samples to describe that distribution of kitties in the universe. Now, if I really do draw 10 samples of kitties, I'm super randomly drawing those. So I'm not really describing this whole data set or this whole general distribution of kitties too much. That's our underlying situation. So when we talk about not enough data, we mean that our data is kind of randomly drawn from the distribution and has some power to describe that distribution, but we are not sure how much power it does, or how exactly it does, or vice versa, how much randomness we still have in that whole thing that we drew. So generally, the first case, what I would like you to consider is the bit more simple case. When you, in general, have enough data, but you don't have enough from one thing. Meaning that, for example, a two-class classifier, you in general have decent amount of data points, except that there is a majority class which is very strong there, and there is a minority class, which is many times the case. I mean, I'm faced with a challenge to predicting from telemetry data when people will crash their cars. That's one of the live data sets I will be working on. Happily enough, people quite rarely crash their cars, and that's very good. I mean, we wouldn't want to have a balanced data set. That means that 50% of the people is already dead. That's not that ideal. So we naturally have this understanding that the interesting things, the real thing that I want to predict is this. I mean, in general, I would say that this is kind of good to have, but My big data situation depends on this, not on the whole thing. So that means that if you look at it from the distributional perspective, many of the classifiers that we use, or we tend to use by default, have this assumption that you have two distributions that are somehow separable quite neatly, because they have kind of a center of mass, which is kind of different. So even with a simple average or simple mean, you would get some meaningful separation. Yeah, I mean, look at that. That means that this is the parallel of the same picture. That means that you have distributions which are, well, in theory, they are different. But if you just really want to draw a decision boundary or kind of a decision horizon, which you explicitly see here, then you will have a hard time separating the red things from the green things, or greenish things, so to say. That is the basic problem here. And yeah, what we can do? I mean, easiest case, we understand that when we use cost functions to optimize our models, we had these assumptions that everything costs the same. I mean, the cost of an error for the majority class is the same as the cost of an error for a minority class. Happens to be that the easiest way to tackle this is just really try to manipulate our cost function in the sense of, okay, it's way more interesting for me when I miss a car crash than I, for example, falsely predict that someone will crash and then don't, because he narrowly survived it. Come on. So on the other hand, from the classifier's point of view, if we pose the challenge in the original way, meaning in the balanced way, that means that this is a perfectly nice solution if he says that category A, 100%. Yeah, sure, but you have 10 dead people. So that's in the sense you are really challenged to modify your objective towards the thing that you really want to predict. It's better to, so it's kind of coming from the design perspective. It doesn't really matter what kind of classifier you use, because even from the experimental design, you could design in that expectation that it's not acceptable to do a minority class error, whereas it's kind of acceptable to do more errors on the majority class. This is kind of the 101 kind of cost-sensitive learning, it is called. And in this sense, yeah, by the way, I always included links to blog posts and or papers in the bottom, so please feel free to read them up. I won't have time to go into each and every one of them, but I would like to put some pointers there. So, suffice to say, one of the basic methods to do this is modify the cost function. But let's think about it. What we are really strongly influenced by in these scenarios is the relative occurrence, the relative frequency of the majority and the minority class examples. To say it in a different way, if I would always compare a pair of the majority and minority examples, if I would somehow balance the number, at least, of the seen examples, I would have a more balanced learning situation. How can I do this? I mean, there is the nice way and the not too nice way to do it. The not too nice way is, I mean, simply undersampling. If I have 100 of the minority class and 10,000 from the majority class, I can simply drop away everything and have 100 for 100. Sounds kind of intuitive, though there are some papers that show us that we here suffer a bit of loss in accuracy. So it's generally a better idea to oversample. In the sense, we take the same examples many more times. So we have 100 minority class examples and 2,000 majority class examples, for example, and we get those 100 examples and use them repeatedly. I mean, kind of repeatedly draw from that amount of samples. Why is this important? Because if we do that, we understand that we are inside a learning mechanism or a learning process. And we can think about manipulating this learning process somehow, or even to understand that we could manipulate the data that we feed the learning process, feed the data, in a sense, a different way. And this is what opens up data synthesis. Data synthesis says that, well, you wanted to approximate some kind of distributions. The distributions will hopefully be not that totally discontinuous, so that there will be regions of space in the feature set that will roughly behave the same. I mean, think about it. Even the simplest k-nearest neighbors classifier presumes that your neighbor is predictive about yourself. So that means that there are regions in space that are themselves predictive in the feature space. So if I try to come up with synthetic examples that are kind of near the original in a certain sense, then I can fake somehow or give additional information about that region of space for the classifier to learn. And this is exactly what happens. There is Moser, which is basically the simple version of doing it. It's starting from n nearest neighbors. Look at n nearest neighbors of the minority class and do a linear kind of interpolation, so do a new data point, which is kind of a linear combination of some of their neighbors. A bit from this, a bit from that. That means that, yeah, these points, these red points over there, which, I mean, can be a bit more spiced up if you do a bit of randomness on top of it. So you not just linearly interpolate 10 neighbors or 5 neighbors, but you add some noise over there. But why? I mean, intuitively, if you think of these methods, these are having this assumption that you fill in a bit of that feature space. So you had some point estimates where you had the original data points, and what you do now is give a bit of information between those with these arbitrary or newly generated data points. There is an intelligent way, kind of a recent publication, which does this with clusters. So first it clusters the data points into bigger clusters, and the interpolation happens inside the cluster so that not to fake some really arbitrary half cat, half dog. So like at least fake the cats from the cats and fake the dogs from the dogs, and don't do like chimera, and because it's, I mean, Greek mythology has these thingies and we don't want to go there. Okay, so this is kind of the basic idea. But again, what we are thinking about is kind of, for me, the metaphor here is a spatial metaphor. That means that we have this space and we want to fill this up. And we could say that, okay, but if we want to do an approximation of a distribution that describes well the majority class, I could recast the problem. And I would say if I have a very good probabilistic model about the majority class, whatever is not probable in that is the minority class. I mean, I can recast the whole thing and forget about classification and say that we have an anomaly detection situation. I have so much of the majority class that I describe it probabilistically well enough and understand that whatever is lying out should be something of interest, and kind of relax that decision boundary that I had to a probabilistic approximation of an anomaly. That means, yeah, if we have a right representation, kind of a representation learning problem, with the right data representation, we already have a very good estimate about how to detect the outliers in a multidimensional space. There are some standard tools that can help you there. But what if we don't have enough anything? Not just a majority class, minority class thing, but we don't have enough data points per se. We don't have enough data. You know that this is like the Rorschach Test. I always see my mother in that because it's just look at 10 points and it's my mother. Whatever psychologists call these, but yeah, literally for that many data points you can fit your whatever on that. Because it's really underdetermined. You just really draw too few samples from that distribution to be meaningful, and this naturally connects us to the problem of overfitting. I mean, if you have that few points that capture or that restrain your classifier, and you choose a decent enough classifier with decent enough capacity, you will fit like hell. over. Meaning that you will be very predictive on these points, but you will be super unpredictive on anything else. What did you do? You took a randomity and you really memorized that randomity with a high capacity model, be it whatever simple model, but if the capacity was too much, then you overfit. So I would argue that having not enough data is very strongly in connection with generalization error, that means overfitting. And I would further on argue that that's why in these not enough data situations, when you generally don't have enough from the data, one of the ways to go is the traditional way of trying to restrict the capacity of your model. Restricting the way of choose a simple model. Okay, I mean, that's 101 restriction, do a linear model that has low capacity. Or if you don't do that, at least do some regularization, either L1, L2 regularization, so that you at least penalize the utilization of the capacity. So you give capacity to the model, but you always give some penalty if it uses it, in the sense. So you restrict the behavior of the models. There are funny things. I draw your attention to these guys who came from physics, and they had the particular misfortune to try to predict some particle physical things with very low amounts. I mean, there are no 200,000 bosons coming up from that big hadron collider. Sadly enough, that there are quintillions of stuff coming out, but 2 bosons. And then you have to get that 2 bosons out of that mess. And in this sense, they really wanted to have some methodology that is principled enough to come up with the most simple explanation possible for the data set. So they went into this Bayesian type of modeling where they really a priori try to penalize the more difficult models. So they are coming up with really the minimal descriptive model that can be utilized. They already did a package of that, so feel free to check that out. And yes, I mean, you can really try some other techniques in cross-validation. You at least can try to come up with a bit more data, so you don't do a big train test split type of thing and lose out 20% of your data, but you do kind of a rolling window cross-validation. That means that during the training you can utilize more of the data set, but that usually doesn't work too much. These things doesn't work too much because the real killer applications are when you have few data, though they would need a difficult model. Because if you have few data in these two-dimensional coordinate systems, well, that's not that bad. If you have few data in a 1000 by 700 pixel kitty space, now that's where the pain comes in. You would need a huge model, but you don't have anything to really tackle that problem with. What the heck you can do? Turns out to be, we have to think about what enough data is. I mean, when I hold my lectures, many times people come up with the question, okay, but how much, what is enough? You don't have enough data. 100, 200,000, whatnot. This guy made a blog post which is decently interesting enough because it's a super simple problem. Super simple. He originally drew 2 circles, 2 concentric circles, added some noise, and drew some samples of it. So what you see here is originally a blue circle, around it a red circle, add some noise, drew some samples. And try to fit a super simple neural network. That's why I want to put there 2 inputs, 25 nodes in the hidden layer, and 1 output. So it's really like as simple as it gets. Like see elegance if you have that. So you have the super small model, and the question is, if you increase the number of data points, I mean, you draw more and more samples from this kind of arbitrarily defined data set, how does the performance of the model change? Interestingly enough, is that he did repeatedly train neural networks, because in stochastic gradient descent, you have some decent amount of variance coming up from the convergence behavior, because it's, I mean, as name implies, stochastic. So what came out is that if you start with 100 points drawn from this distribution, it's not just that the mean precision is low, it's very varying. So that means that if you don't have enough data for a big enough model, you don't just have the problem that you will have low accuracy, that you have don't know how much accuracy. So that, I mean, I was more frightened about the size of this box plot, not the mean, which was really, really low. That means that if I have a problem which converges for a week, and it converges, and it has a low error, then I don't even know what the heck is going on there, because it even can be that it's kind of arbitrary, and I've ended up somewhere over there, and why? It's not my day. Okay, so what happens? Yeah, I mean, naturally, because this is a super simple problem, I mean, you could really draw a circle around it and separate the whole thing. It turns out to be that in this super simple case, you at least need 1,000 examples to get a nice behavior, and yeah, as you see, the box plot collapses, so that the individual models are not that much different from each other, and there is a very, very slight increase when you increase the data more and more. But there is somewhere an optimum. I think the guy wrote that there is around 2,500 examples, you will have kind of an optimum behavior. But that means that we generally could rephrase the amount of data as a kind of regularizer. Think about it. If I stole this from Professor Moser, who argued that one of the basic and fundamental successes behind deep learning is that we use a huge regularization, the data sets. We use 10 times bigger data sets. That means that it's 10 times more difficult, roughly, philosophically, to approximate those with, kind of overfit those with a model. So one of the big issues that may help deep learning succeed, because that's always the big problem. I mean, why does deep learning work? We know that it does, but we don't know why. I mean, the argument of Moser was that one of the factors is exactly this. So if you see that there is this behavior of train error and test error, whereby the red is the train error and the green is the test error, and there is an optimum somewhere over there, and from there you get overfitting. What you can do is add more data. That means that it shifts the balance of the whole thing. So yeah, throwing data on the system, it naturally helps the system in the sense to do less of a rubbish or less of an overfitting. Now, how can we operationalize this? Everyone needs kitties, every presentation needs kitties, so we do have kitties here. One of the basic things to do, naturally enough, and people do it in image classification, is that you generate arbitrary augmented data. As in the Edison example, Edison, what did it do? It was a linear interpolation of stuff in the feature space. You have to rephrase this whole thing. You can do data augmentation in the original space. So you can crop kitties, you can rotate kitties, you can do whatever, sub kitties and half kitties and whatnot. Importantly enough, that, and this is what people don't really talk about, these transformations of the data should be at least plausible in the visual field. I mean, if you do an inversion of the kitties, that doesn't really happen. I mean, technically it's a transformation which is possible, and technically it would augment your data set. Just technically you won't observe it anyhow, because there is no such thing as color inversion in your normal feature space. I mean, hopefully you don't get up in one morning and you see inverted colors, because you would really be scared at that day. So yes, absolutely. What happens and what should happen is that you, as Mickey will demonstrate, you can do realistic transformations on the data set to get to a bigger data set, and that would hopefully increase your model accuracy. Now, there are some ways to do variations. In this, data distillation on the one hand is the solution where you get the original data set, train a classifier. You do a bunch of rotations and train a classifier. You do a bunch of cropping and train a classifier, and so on. And you get these classifiers, and as we know, ensemble methods always work. If you get 10 classifiers and somehow average over their performance, that would increase a bit more than when you would do the rotations and stuff first and train a one classifier system on top of that. So sometimes people use this kind of transform model, ensemble, predict type of thing, getting some couple of percentages more out of the models. And on the other hand, what is really surprising is weak supervision. This comes from Facebook, is that even the understanding is that even if you have 1 or 2 orders of magnitude bigger amount of data, though you know that the noise in the data set is way worse, it will work better. Let me give you an example. If you go for, I think, ImageNet as a data set, and you go for another data set, which is coming from scrapes from Flickr or so one of these photo sharing sites. I don't know the name, whatever. People share photos and do hashtags under it. That's the big idea. And Facebook scraped gazillions, really, I think like hundreds of millions of images from that. But we know that people just really do random shitty hashtags under it. So I wouldn't say that it's a properly annotated data, you see. And it turned out, because your expectation would be that the major factor for the data is the proper annotation. But it turns out that the amount of well annotated data performed way better than the smaller amount of properly annotated data. Because, again, I don't know, so I cannot prove, but the intuition behind it, again, for me, is that you have a spatial distribution, and even with shitty labels, you fill out that space between the classes a bit more from having some kind of rubbish, half rubbish, more truth than rubbish type of thing. And even you get some kind of gradients, not good gradients, but gradients. And it's better than nothing. So that you learn something from that general distribution of stuff happening in the universe. Some people took this example on a different path and tried to operationalize it. Side note, and this is, I mean, purely the only reaction I can say, what the fuck, is that people train some models. This is kind of a recent paper, came out some couple of weeks ago. Train some models on MNIST. You know, MNIST is 60,000 images of handwritten characters, and 0 to 9, you have the handwritten digits, and you have to predict the digits from the 60,000 characters. They took the 60,000 characters, trained a kind of simplish convolutional neural network on top of it, with kind of good accuracy, then took that final model and synthesized some images via a gradient procedure, very reminiscent of the feature visualization like ZFnet, like Zeller and Fergus type of thing. So they generated arbitrary bullshit images, in the sense the prototype images for the 10 classes, 10 images, then took that 10 images, fired up a new model, trained it on that 10 images, and it performed nearly as well. What the heck? Meaning that these rubbishes, this 10 rubbish, contains the freaking 60,000, the information content of the freaking 60,000 examples. What? Caveat that it's in connection with specific architectures. It doesn't work if you change the architecture. That means that there is some kind of unholy alliance between your architectural, the distribution that is presupposed by your architecture, and the distribution what is in the data. And this kind of unholy alliance makes the data super compressible. And again, I have to state, what the fuck? That's the only scientific commentary I can give you at this point. What the fuck? So watch this field, something is happening, I don't know what. I looked at the paper and said, bullshit, and then closed the paper. What? Again, closed the paper. I did this 3 times, but then I couldn't resist to present it to you. So anyhow, there is something going on. Back to the main topic. What our understanding with the noisy labels is that you want to approximate that distribution of possible kitties in the universe well enough. Okay, what you can do? What you can do is called Mixup. Mixup is, I think, a year ago, came out a year ago or so. Mixup says that even in the case of a classification problem, blue, red, that was the original classification problem. Do some new data, like arbitrarily synthesize some data, as well with another scene and the other things, but with new labels. Look at that. I would have, like, 1 would be blue and 0 would be red. And what I do is I put here half blue, half red type of things. I generate new labels. I kind of go back to a regression problem, if you want. So kind of degenerate the classification problem, do a very ugly and seemingly unintuitive regression problem out of it. That means that this chimera would be a 60% kitty, 40% doggy type of non-existent, what the heck. But it's very easy to be synthesized because you get 2 examples from 2 classes. I mean, do a weighted sum of those things in the feature space, and you assign a new random label. No, not random label. I mean, you assign a new label that exactly represents that amount of weighting that you did, and there you go. You can do explosively more examples for whatever you want. I mean, pre-compute these examples the hell you want, and then let the classifier converge. It does help. It super strongly does help. That means that, again, what we come up with is that we are not restricted to this information. We are learning something from this space between the 2 things. And I would argue that inside generative adversarial networks, the same is happening. Because there is this distribution that the forger always tries to attack at certain places. With arbitrary small changes in the z vector, I mean in the latent vector. So it kind of taps everywhere. So the discriminator is forced to tap into these noisy parts also of the data set, not just the proper ones that we observe. And this again comes back to the fact that we are having a finite sample from an infinite amount of kitties. Okay, let's go a bit more. I would argue again, and that's why I a bit went into the direction of generative adversarial networks at all, is that transfer learning in itself is also kind of a data augmentation procedure. Because even in a linear regression case, what I had to realize lately is that the model itself is containing implicitly inside the weights, I mean inside the parameter space, some knowledge that has been extracted from a certain data set. So yeah, I mean one of the natural ways to attack a problem where you don't have enough data, go for another problem that is super similar, learn something and try to apply that knowledge here. Try not to forget everything. Try to avoid catastrophic or forgetting. There are these good techniques with gradual freezing and unfreezing in neural networks. See, for example, Ruder, who is doing this UML fit type of thing. But with decent enough tricks, you can transfer some of the compressed knowledge inside the model to another domain. So you had few data in your domain, and ta-da, you were able to get some other knowledge. And interestingly enough, and that's what I argue again, is that all the models that presuppose a distribution, in a sense, variational autoencoders or generative adversarial networks, are prime examples that are very well suited for transfer learning. because they already approximated a big distribution of stuff somewhere in, for example, the visual space, and you get that distribution and try to specialize your data on top of it. So I would argue that you could really technically utilize these models to enhance your situation if you have not enough data. Moreover, there is a simple case where I have to say, yeah, you have a tricky data set. My favorite tricky data set is with the chihuahuas and the muffins. Everyone knows it. I mean, sometimes even I mislabel that. I mean, what the heck? Like, in this case, I don't know, what the fuck? Okay, so there is the obvious solution for this, is that ask for it. You know, that pity joke with the death list of the bear. Could I get out of it? Yeah, sure. Pfft. So I don't have enough data. Please give me some more. Okay, why not? So you could anytime try to get people to label your data set a bit more. But if we understand that there was these partisans, or I don't know how to call them, who could compress that freaking MNIST to 10 examples, that means that it's totally not obvious which examples people should label. They could go there and label 200,000 uninteresting examples for you, which is kind of good work, costs a lot of money, but doesn't help. On the contrary, they could maybe help you annotate 10 good examples that would help tremendously. And in this regard, I think this is the intellectual justification for active learning. Active learning, where you really look at the classification uncertainty given a data set. So you train a classifier on a labeled data set, you look at unlabeled data, and you look at the really kind of non-intuitive or in the cases where the model doesn't know. When the model is kind of 50-50, where the model is really low in probabilities, and ask for that specific things to be annotated, because we could argue that it gives the most information. If it's kind of the prediction is 99.9% kitty, I mean, why ask? Ask something that is more interesting, that may you learn something. And again, if you think about the spatial metaphor, that means if something is very close to one of the, in a distribution, one of the known things, I mean, the neighbors are super close, that's an uninteresting thing. When something is really far away from everyone, that's the thing that you want to ask for. So I would rather say that this is the same metaphor, just applied in another way. And again, ask for what? Please consider again the business objective of what to ask, because if you have an unbalanced case of, yeah, you're 90% accurate, but that means that from 110 people are dead, please, pretty please ask for those things to be annotated that are of interest. I mean, that are of the business interest. So if you can have, and this combines back to the minority class stuff again, so ask for the interesting parts. But my takeaway is that if you think of these distributional problems, you can construct a pipeline where you ask for the interesting stuff from the business perspective. You involve the users with minimal feedback but with maximum effectiveness, just because you understood that you are choosing the right things to ask for, and you will be able to, as far as I understand, radically increase the effectiveness of your models, and most importantly, not piss off your users. Because if you say that you are still super valuable to give me feedback on 10 interesting things, via you are fired and the classifier will do everything, that's, I think, a better message even. So there is the added benefit of not pissing off people if you involve them in a constructive way to give a very dedicated, intelligent feedback. So that's, I think, the total takeaway from my part. If you go back to situations and inside corporates, you will find not enough data. And one of the solutions is that involve the users with good feedback and think about these distributions and try to use the tricks constructively. Thank you very much.